I'm guessing the double aspect addresses that limitation?
You guessed right. With a doubly linked list, you gain the ability to move both forwards and backwards through the list.
How?
The crucial addition is that each node, besides holding the data and a pointer to the next node, the next pointer, also contains an extra pointer that points to the previous node in the sequence. This is often called the prev pointer.
Ah, a previous pointer too.
Exactly. This prev pointer is what enables you to navigate backwards easily. Think of it like having both next and previous buttons available on every single item in the list.
Okay, so each node now has connections or pointers to both its successor and its predecessor in the list.
Correct.
The source shows an example with the numbers 7, 4, and 9.
Right. In that illustration, you can see that the node containing 4 has a next pointer going forward to the node with 9, and it also has a prev pointer going back to the node with 7.
Okay, I see it.
And just like before, there's still a head pointer pointing to the first node containing 7. The blueprint for a node in a doubly linked list, as the source shows, now includes 3 fields: prev for the previous node's address, object for the data itself, and next for the next node's address.
Makes sense. So, what are the big advantages of having these previous pointers? Why add that extra complexity and memory overhead?
Well, the source points out several key benefits that often justify the extra pointer. The most obvious one is the ability to traverse the list efficiently in both forward and backward directions. This provides much more flexibility.
Okay, flexibility is good.
It also makes certain operations much easier. For example, deleting a specific node when you only have a pointer directly to that node becomes simpler. In a singly linked list, you'd first need to find the node before it to update its next pointer. In a doubly linked list, the node you want to delete already knows its neighbors via prev and next, making the relinking easier.
Ah, because the node itself holds the addresses of both neighbors needed for the bypass.
Exactly. And similarly, it simplifies the process of inserting a new node before a specific existing node. With the prev pointer, you can easily access and update the necessary links without having to traverse from the beginning just to find the node that needs to point to your new node.
That makes sense. If you need to go backwards frequently or insert delete efficiently given just a pointer to a node, having those direct previous links saves you from potentially having to start from the beginning of the list every time, which could be slow for long lists.
Precisely. It often makes the implementation of those kinds of operations cleaner and potentially faster, despite the extra pointer per node.
Okay. Now, the source provides a really detailed example of inserting a new node into a doubly linked list. This sounds like it involves some careful pointer juggling. Can you walk us through that process?
Absolutely. It's a great way to see the mechanics. Let's say we have a doubly linked list that looks like this. 34 is linked to 45, which is linked to 9. So 34 into 45 to 9. And we want to insert a new node with the value 25 in the third position. So the goal is to make it 34 into 45 and F25 into 9.
Okay, slot it between 45 and 9.
Exactly. The source breaks this down into a series of pointer adjustments. It's like careful surgery on the links. First, they suggest using a temporary pointer, let's call it temp, and moving it to the node before where we want to insert, in this case, the node containing 45, which is at the second position.
Okay, temp points to 45.
Right. Then you create your new node, let's call it new node, with the value 25 inside it. Now we need to start setting its pointers. Its previous pointer should point back to the node temp is pointing to the 45 node. So new node.prev temp.
Got it. New node points back to 45.
And its next pointer will eventually need to point to the node that comes after the insertion point, the 9 node. To keep track of that after node easily, the source suggests using another temporary pointer, maybe temp2, to point to the node that used to be after temp. So temp2 equals temp.next, which points to the 9 node.
Okay, I'm following. We have temp pointing to 45, new node holding 25 and pointing back to 45, and temp2 pointing to 9.
Exactly. Now comes the crucial pointer rewiring to link everything together. We need to make the 45 node point forward to our new 25 node. So we update the next pointer of the node at temp.next new node.
Okay, 45 now points to 25.
Okay, now we need to make the 9 node point backward to our new 25 node. We use temp2 for that. temp2.prev is new node.
Right, 9 now points back to 25.
We're almost there. We just need to set the forward pointer of our new node. It needs to point to the 9 node, which temp2 is pointing to. So new node.next, notice temp2.
Okay, 25 now points forward to 9. The circle seems complete.
Almost. We set new node.prev earlier, but sometimes it's done here. We have new node.prev pointing to temp45, new node.next pointing to temp29. We have temp.next, 45's next, pointing to new node 25, and we have temp2.prev 9's prev, pointing to new node 25. Now all the links should be correctly established.
Wow, okay, that's quite a bit of pointer manipulation. 4 pointer updates in total, it looks like, to weave that new node in.
That's right. 2 on the existing nodes, 45's next, 9's prev, and 2 on the new node, 25's prev, 25's next.
But I can really see how that correctly weaves the new node into the middle of the list by just updating those addresses, those links, without needing to physically move the 45 or the 9 or anything else in memory like we had to do with arrays.
Precisely. That's the beauty of it for insertions and deletions. You're just redirecting traffic, not rebuilding a road.
Oh,
The source likely provides a visual step-by-step to really illustrate how those connections are reestablished. Yeah, that detailed explanation really makes the insertion process in a doubly linked list much clearer, even with the pointer juggling involved. Now, the last type of